So hello, everybody, and welcome back from the break. This is our last session of the Unconference on moving beyond continual learning. So it's my pleasure to introduce Emtiyaz Khan, who's a tenured team leader at the RIKEN Center for Advanced Intelligence Project in Tokyo, and he's leading the approximate Bayesian inference team. He's an action editor for the Journal of Machine Learning Research and has served in the organization and reviewing of most major machine learning conferences. He has many foundational works in Bayesian continual learning, and we're super happy to have him here today. So without further ado, Emti, the floor is yours.
Thank you. Can you hear me well? Is it good?
It's perfect.
Okay, and you can see my slides as well?
Yep, yeah. We see you, we see the slides, and we can hear you.
All right, awesome. So thanks a lot for organizing this unconference and also inviting me to give this talk. This is maybe the third time that I'm giving this talk, so it's getting a little bit better. But the time, I think, is a little bit less than what I usually do. So I may have to skip some parts in the end, but hopefully I'll get to touch upon the most points that I want to say about how to build machines that adapt quickly. So the slides for this talk, you can find it on my website. So please go check those out. So when I talk about building machines that can adapt quickly, my motivations come from human beings, specifically a human being that lives with me. So this is my daughter when she was 6 months old. She's now 8 years old and can do many things now. But at the time when this video was taken, she was still kind of exploring the world, trying to figure out one thing that she really likes, the sound that comes from this ukulele. And what has, really amazed me, and of course we know this, that kids, as they grow up, they learn more and more. So this was like after 6 months of, exploring the world randomly here and there, and then converging somehow to figure out that the interesting part of the world lives where this nice sound that comes from it. And it's quite amazing how, humans can actually figure out interesting things in the world that they are, they would like to have more of that experience. And not only that, like if you change the environment slightly, then human beings can adapt in a innovative way. So here, going from ukulele to guitar, which is slightly bigger, this human being has adapted herself to get the same experience that she has enjoyed in the past. This is something that I'm very interested in. How can we build machines that can have this kind of adaptive behavior, quick adaptation? And currently, we don't really have anything that comes anywhere close to it. So in robotics, it's very easy to show that if you have a robot, it's not as fluid as human beings, as little kids. If you change certain things around in the environment, the robot cannot very quickly adapt to it. So sometimes the system can be too slow to adapt, but then sometimes it will be too quick to overfit to the new data. So this is before GPT, many years ago in 2016. So Microsoft was still trying at the time to put a chatbot, an AI bot, and they put something on Twitter. And this bot was manipulated within 24 hours to say many racist things to people because it adapted too quickly to the new data and forgot the old knowledge. So there is this tension between preserving the old knowledge and acquiring new knowledge, and somehow doing this in a flexible way. Because human beings, animals, they can do it much, in a much better way. And in machine learning, we don't have really any good mechanisms to do it. So right now, the state of adaptation in machine learning is that even a small change that you do in the system, so like you change data slightly, or you change training loss, or model architecture, or perhaps some hyperparameters, or maybe you want to use a different algorithm. Sometimes even slight change in infrastructure may lead to a completely different solution, right? So small change it may require a complete retraining from scratch. And this leads to a huge amount of resources needed to be able to kind of do this kind of retraining. So if you have to train your, GPT like every year and throw $1 billion at it, it's not going to be very sustainable and also not environmentally friendly, and only some people can afford to do it. So this is not acceptable. And if you want to apply this kind of system in a more dynamic setting, like in robotics, in medicine, in epidemiology, where things are changing over time, and you still want to adapt to how things are developing, then it's you can't keep retraining it all the time. So it makes these systems be very limited. So my goal has been to solve these challenges. And I truly believe that if, while solving these challenges, we should also be able to reduce some of this magic in deep learning, like everything somehow works when you have everything, all data at once in bulk, and you throw all the compute at once, and then somehow things naturally emerge in the model. But we don't want magic, we want science. So my belief is that if we work on this adaptation problem, if we're able to solve this, then we're also able to understand the value of new information in deep learning and how it's being used in the model. So, we've been working on this for a few years now, and today I will try to maybe summarize a few main points, 3 of them. So how do we build machines that could adapt quickly? Well, we want these systems to have better uncertainty. We want them to have better regularization capability, meaning that they should be able to transfer past knowledge to the future. They should be able to regularize the future according to the past. And they should have better memory, meaning that they should somehow remember a good representation of the past that can be reused in the future. So there's 3 components: uncertainty, regularization, and memory. And I will present one solution for each of those. And these are really generic, like principled, foundational things that we have discovered, and we have given specific names to them. But they are basically general principles that connect a lot of things that already exist in the literature, but then use them in a novel way to get to quickly adapting machines for modern, machine learning methods. So there are 8 references here. Most of these are out. So what I'll present is mostly covered in there, and hopefully the talk will give you a way to kind of go through these papers and figure out what we are trying to do. Okay. So let me start with the example. So when I was introduced, I was told that this session is about going beyond continual learning. But let me start with the continual learning example. So this is one type of adaptation, right? So in standard deep learning, we have all the data at once. We randomly select few images from this kind of big ImageNet data set, for example, and then we update our deep network. So this is kind of bulk training, and we want to go beyond this and go into a setting where maybe the information arrives slowly over time, and no matter how it arrives, in what order it arrives, we are still able to kind of match the performance of the deep learning framework that I'm showing you here. So continual learning is one such setup where you say past classes are never revisited, for example. So you see dogs and cats, you update your network, then you see lion versus tiger, and then you update your network, and you keep on doing that. And the hope is that you more or less don't have to revisit old things. And right now, if you do this, somehow that this leads to catastrophic forgetting. So this example we'll use throughout the talk, and this will help us to understand some of the principles and how we can design quickly adapting machine. So the first piece that I'm presenting here is about uncertainty. So how can we get better uncertainty to improve the adaptation? So I'll talk about this work that we have done on using Bayesian principles, leading to an algorithm called Bayesian learning rule. And you can use this to, in a straightforward manner, to improve some aspects of continual learning. So, well, the standard way that kind of started this whole field, restarted this whole field recently in 2017 is to use this elastic weight consolidation weight regularizer. I believe most people in the audience know about this. So you have this kind of quadratic regularizer. You have an old model, and you basically want your new model to be close to the old model, and you're adding this regularizer where you're using this weight uncertainty. So this could be something like a Fisher matrix or a Hessian matrix, or maybe some kind of covariance matrix that represents your past uncertainty. Right? So the straightforward way to improve this is to simply use better methods to estimate this uncertainty. One idea is to use variational inference. And we've done a lot of work on this in trying to scale up variational inference to large deep learning models. There's 3 papers that I have shown here. Essentially, what these works do is that they try to extract this kind of reliable estimate of Fisher or Hessian or some kind of variance information about the parameter from a deep learning algorithm like RMSProp. Okay? So I believe most of you are familiar with RMSProp, but you don't really have to know exactly what's written in this slide. But essentially what I'm trying to show is that you compute your stochastic gradient and you do some kind of square of the gradient. And this is a kind of, you could see this as an approximation to the Fisher. It's a very bad approximation. So you could actually just use this S matrix if you wanted in that weight regularizer. Commonly, people right now would train the network, and then they will do another pass through the data to compute an online sort of estimate of the Fisher. But that takes like an extra step, and it's also hard to make sure that it's well conditioned, meaning that it's regularized. So when you add this as a regularizer, it gives rise to good performance. So this could be an issue. What we actually suggested is to use this Bayesian learning rule based solutions, is essentially trying to do something like variational inference. And it turns out that when you apply this Bayesian learning rule to a variational inference objective, you get something that looks almost like an RMSProp algorithm. So it's line by line, it's the same. There's few parts that are different, which are shown in red here. But essentially what you do is that the main point is that instead of computing this G square, you perturb the gradient by some epsilon. And this sort of gives rise to some kind of Hessian information. So this H is now truly computing a Hessian. And then you are somehow doing a weighted moving average of it. You add a term so that this Hessian never goes to 0. So this term makes sure that it's always well conditioned, because Hessian can be negative sometimes, but S is always positive, you can make sure. And then you can use the inverse of the S as the variance. So this is kind of one way to get a good estimate of the Fisher or Hessian or variance by simply training using RMSProp-like algorithm, but slightly changing it by perturbing the gradient, you're able to estimate Hessians more faithfully. So if you want to be really Bayesian, then you can also perturb around the mean, just like sampling from the Gaussian, but it's not really necessary. So my point is that the cost of these two algorithms, they are exactly the same. There is very little overhead, like maybe 1 or 2 vector multiplications that are added, but it's almost, complexity is almost the same, and costs are almost the same also. But the variance quality that you get out of this algorithm is it's a lot better. Actually, just to convince you of that, I show some numerical results here. Don't have to look too much into it, but this is like CFAR 10, standard continual learning task. So x-axis is task and y-axis is accuracy. Higher is better. And these bars are basically showing what you get if you do joint training. And if you actually do straightforward variational inference, it's this orange-yellow thingy here. This is actually quite bad, right? So this is the variational continual learning. And if you do EWC, it's actually reasonable. So it's this guy here. But if you do this BLR, so one variant of BLR, which we call Vogan, so it's like a Gauss-Newton approximation instead of Hessian, so it's more like Fisher in that sense, then it already improves over EWC. So you can see here improvement that is obtained over EWC in all of these tasks. So it does actually work, and we have shown this on really large problem like ImageNet. Also, this method works and gives quite comparable results to using Adam and other optimizers. If you like this work, there's a very nice paper that we wrote in 2021. It's now accepted. But essentially what it shows is that all sorts of learning algorithms in deep learning, in optimization, they can all be obtained as specific instances of this Bayesian learning rule. I only talked about RMS-prop Adam today and how you can use this variational online Gauss-Newton. So this is like method to estimate the Fisher or the Hessian. So that's what I showed you right now, but there are a lot more that you can do with this. Okay, so that was the first part, straightforward solution to improve continual learning by just simply estimating the uncertainty, weight uncertainty better. So this is working in the weight space. Are there better solutions to this? And that was the question that we were asking a few years ago. So can we have better regularizer than just using a quadratic regularizer? And some people actually argue that, oh, these experience replay methods are using sparsity or masking. These are not regularization methods. So, you know, perhaps we should be doing something else other than just using the weight regularizer. But essentially, what we found in our work that all of these, methods like replay or using weight regularizer or using some other kind of knowledge distillation style thing, they're all some kind of regularization method, and they can be written in a more general form that we call knowledge adaptation prior, or K-priors in short. So I'll try to explain in the second part a better regularizer than simply using a quadratic regularizer. Okay, so here, essentially, the main idea is in this regularizer, we don't simply just use a quadratic regularizer in the weight space. Rather, we try to go into the function space in terms of like how the model is predicting, and then try to freeze those predictions somehow. An illustration is shown here. So let's say you get the first task and you have a binary classification problem. You learn a model. This green line here shows the uncertainty around it. What you can do is actually you can try to find some points, some data examples that are really crucial to preserve this line. So it's kind of like putting some pins around this thread so that the thread doesn't change much, or at least doesn't change in this location. Okay, that's the kind of idea that you want to now take these points and you want to regularize them so that you don't forget in the past. So then when the next data set comes in, so this is task 2, you may try to now learn a line that explains this data, but it somehow also preserves the performance on these points that you have frozen, right? So this old knowledge is somehow in these examples is preserved. We actually call this a memorable example. Like these are the examples that are worth remembering from the past, and we want to regularize them so that the prediction in those examples don't change much. So functional regularization of memorable example, or FROMP in short, means exactly that. So then you again do the same thing. You freeze new points, and then when you get the third task, you draw another line, such that this past and future somehow kind of performance is maintained. Okay, so I hope you get an idea, and I'll show you the math, and then we'll try to understand why this thing works and why is it a better regularizer. But before doing that, let me just show you the performance that I showed before, right? So when we did the Bayesian learning rule, the Vogan in previous slides, we got performance somewhere here, right? This red thing. But now, if you did this functional regularizer, this is this purple line. It actually consistently it's improving in every task. So it does kind of do the right thing. And we would like to understand why actually this happens. Why does this kind of regularizer is working better in this case? So let me try to go through this and try to make sense of some of this things that I've just said. So in weight regularizer, you are completely working in the weight space. What we actually did in this paper, and we use lots of complicated Gaussian process ideas to write down this regularizer somehow in a function space. So in a function space, meaning it's in the network output. So let's say F is the network output, and sigmoid or softmax is the actual prediction. Then what we are actually doing is that we are making sure that not just that the parameter is close to the old parameter, we're now saying that the predictions of these parameters are close to the old prediction. So it's kind of a mathematical way to write what I showed you, that the line is still predicting the old examples well, right? So there's actually two parts to it. So one is making sure that the predictions are close, but then we also have a kernel. It's pretty much like this Fisher that you have here. And this kernel is then weighing the different predictions. So like some examples that are maybe very crucial for the future, there maybe the weight should be higher. And the examples that are less important for the future, the weight should be lower, right? So this equations should automatically sort of do this job. And these are the reasons why actually this is kind of working well, but it's not clear why this explicit form is used and how it's related to this weight regularizer. If you just look at it, then it may not make sense right away. Okay, so this is kind of a question that we've been asking for some years, and then in 2021 we had some answers to this. Why does this kind of method work? Well, it turns out that you can actually show that both of these regularizers actually they can be seen as a way of reconstructing past gradients, meaning that if you simply stored old data and just recomputed the gradient on that old data, instead of storing the data, you could just add the regularizer, and somehow this regularizer is also reconstructing those gradients. So it's actually quite similar to experience replay style of things that are being used. So we have now like a whole theory with this knowledge adaptation prior, K-priors, to show that you can actually write these regularizer in a more general form that will encompass all of these, like weight regularizer, function regularizer, and memory replay, and all of that other stuff. Okay? So I think if you understand these points, and if this gets through you, then I think you know mostly what I'm trying to say, and the rest of it is kind of detail. And okay, so I've used 23 minutes now, and I believe I have about 12 more minutes or 15 more minutes to go. So I will try to go through some equations. So I have only one slide with quite heavy, equation and a little bit of math, but I felt that if I can convince you of this example, maybe everything else will kind of be very, very concrete for you to understand. So essentially, I want to make this point that I just said here, that these regularizers, they're essentially doing very similar things, but they're just different ways to somehow compute and replay or reconstruct old gradients. So I'll formalize this a little bit more just for linear regression. It's the easiest problem that one can work with. So let's take this linear model problem. So theta is the parameter, and I have a, let's say, L2 regularizer, with just 1 is the regularization parameter. And I have a loss, it's a quadratic loss. So Y is the regression like output, and X is the feature matrix. So this is in somehow in, if you want to think about it, in this objective, the regularizer is in the weight space, and the data is somehow, it's in the prediction. So it's in function space, right? So you already see that there are 2 parts to the problem. And if you take the second derivative of this, you can compute the Fisher. So Fisher and the Hessian are the same thing. Covariance is also the same thing in this simple example. But essentially, if this was the old problem, then the Fisher would just be second derivative of this, which is just identity, second derivative of this, which will be X transpose X. So it's a kind of parameter, it's a Gram matrix, essentially. Now, if you use a weight space regularizer, it looks like this. This is entirely in weight space. But actually, you can rewrite this in a slightly different form. Okay, so in this case, you can simply plug in the Fisher. So Fisher is this. You plug this in, and you see that this has 2 parts, right? One comes from the weight space, the other one comes from the function space, and you just kind of push these things in. So the first term, I, just gives you a weight space regularizer. And the second term, because X multiplied to theta is the prediction in the linear regression, so it's just simply this, you're now comparing the prediction. So actually, in linear regression, you can interpret EWC as just doing also weight space regularization, but with the regularization parameter set to 1. And also matching the predictions. So I want the predictions to be same as old prediction that I had. I don't want them to change much. And that's what we're trying to say. Okay. So you see that there's very little distinction between weight space and function space in this sense. And what you can actually do is you can use some kind of duality, and you can rewrite this completely in the function space also. So you can write this in terms of X theta and X theta old. So in terms of prediction, K would be then some kind of kernel, which will be dual of this matrix F. And this is well known in kernel methods in Gaussian process community. I'm not going to go into detail of this, but what I'm trying to say that in this simple example, all of these are same things. So there's no distinction between function space and weight space. Okay. What we actually are doing is we are saying that this representation that you have in the middle here, it's a little bit of a better representation because it has both weight space and function space kind of put together. So we call this representation to be knowledge adaptation prior. So really, this is what is going on in this work, is that we are trying to somehow write this down in a better form. So we suggest that one would write it like this. In linear regression, these are all equivalent, but if you go to nonlinear problems, then some are better than the others in different contexts. Okay, but they can all be seen as reconstructing somehow the old problem. So actually, if you did a little bit of more math, like if you added plus and minus y here, you can actually show that this is just a rewrite of the original problem. Okay, so it should not be that hard for you to think that the gradient of all of these quantities objectives are equal. They're all ways to recreate somehow old gradients. So that's the main idea, and I will not go too much into the detail, and you can read the paper for that, but I'll just present the more the general form. Essentially, we in the more general form, what we say is that you can write a k prior as a term that is in the weight space. So you're saying that your parameter should be close to your old parameter, but then some of it is in function space, meaning that you're saying prediction should also match. And this is a more general way of writing these things down. If you want to see it on a simple problem, like let's say if you have a 2D classification problem and you have an old model, so let's say this is the old model, then you are trying to basically say that when you have a new model, let's say this in blue, you want this parameter to be close, but you also want the predictions, let's say in these locations, let's say 4 of these locations, you want these two models to not predict that differently, right? So because this point is on the same side for both classifier, and these points are on the other side, so they're actually agreeing on the prediction. So maybe this is a reasonable candidate model. So something like that is what is going on here. So k-prior is in that way. What we show in the paper is that if you compute the gradient of this, you can show that this is related to the gradient of the old problem. Okay, since all this math is written in the paper. Okay, so I have 15 more minutes. Let me so I have some visualization. Maybe I'll do very quickly for you to maybe get a little bit more intuition about this. So let's say you have a classification problem, you have this problem, and then you got the new data, and your model changed from this dashed line to here, right? So now this black model is the correct model. And before, your classifier was like this, and I add the data, and your classifier moved because you have some data here, some data here, okay? Now, what actually all of this stuff is trying to tell you is that when you go from here to there, some of the points in this old data are being affected, right? Because the line is like coming very, very close to some of this region. It's going to change and go to that place. So essentially, what it's telling you is that you should try to make sure, if the change is like this, you should try to make sure that your predictions for these points have not changed that much. So these points are the most affected point by this change, and you should try to make sure that the predictions don't change. If you do that, then you can kind of recover the line faithfully. On a simple 2D problem, you can actually see it as you increase the past location where you're trying to match the prediction. So this is a 2-dimensional problem. So this is in parameter space. The true optimum is here. And as we add more data examples, the minimum is somehow converging to the true, and the gradients are all kind of aligning to each other. Okay. So we have another paper now, which I am not sure if it's online, but if you search for this, you may be able to find some copy of it. But it's very recently, maybe 2 weeks ago, accepted at TMLR. Essentially, there we use this methodology to show how can you combine EWC with functional regularizer and replay together. And essentially, the idea is to figure out how much gradient error is made by EWC, then correct that by adding a functional regularizer term, and then further improve it by adding a replay term. So then you see that as you add these terms, the gradients are kind of becoming better and better. Sorry, I'm not taking questions right now somehow because I cannot see them, but I see that there's things in chat, but I will get to it in the end. I hope that I have some time. But in the last maybe 5 minutes or so, let me try to tell you the last bit of this, which I don't have much detail about this, but essentially in all of this part, you can see that somehow when your problem is changing in the future, some of the points in the old data are affected, right? So those points, you want to make sure that your predictions are matched, or your gradients, for your gradient to be reconstructed well, those points are the most crucial. So then this is the third part. If you choose better memory, better representation of the past, you're able to somehow do this transfer task better. So how do you choose those points? Because you don't know the future, what's going to happen in the future. So you want to pick them somehow that they are more or less good for most of the changes that you would expect, right? So the third part is about figuring this out without knowing the future. How can I pick my past data examples so that the gradients are reconstructed better in general? So better memory. And the math is actually quite straightforward. So you essentially just go and look into the gradient reconstruction error. And if in neural network problem with this kind of let's say classification loss, you usually would see this kind of k-prior like front-like regularizer, as I said before, that you're basically trying to make sure that the predictions are matched, right? So these are two predictions. And this term, it turns out, is related to the prediction error of the old model. And this is what it comes out to be. I'm not going to go into the detail of this. But then what matters is that how diverse these examples are. So like if you have 2 points at the same place, then you don't have to consider all, both of the points. You can only consider one of them, right? So that part is taken care of by features. So you only, if you have a handful of examples from the past, you look at their features, their Jacobians, and then you see that you only need to pick a handful of points so that all features are represented well, right? So there are two components. So this is the thing that I showed you with front in the beginning. There's a kernel and there's predictions. It's essentially the same thing formalized with k-prior. So the general message here, without going into the math, is that somehow there should be past and future agreement, and you can there's no general rule to make sure that you can always ensure that these things agree, because you don't know the future. You can just choose points that are somehow your current problem is very sensitive to. So some of the examples that are predicted that have high prediction error, or some of the examples for which there's high predictive variance, you can choose those points and store them. And you would hope that these points would be a good representation because of this theory that is being shown in this slide. Okay, it's sort of hard point to wrap your head around. So I show you a picture and then I'll close the talk with this. Essentially, what you can show actually is that the model deviation, like how much the model is going to change when you add new data or remove data or you change the problem, you can show in simple problems and now in complicated problems as well, that the change in the model is almost always proportional to the prediction error of the data example and prediction variance of the data example. Okay, so intuitively, what I'm saying is that let's say you have an old problem, and in the future, perhaps you add a data example or remove a data example, you change it. So you perturb this example. So if you move this example far, it becomes harder to predict for the old model. And what the theory predicts is that if the prediction error is high, then the model change is also going to be high. If the prediction variance is high, meaning that the point is quite far so that the variance is, you're not very confident in predicting it, then also the model is deviation, the model change is going to be quite large. So the model change is shown here in blue and the variance is shown in red. Okay. All right, so with this, I think this is kind of the idea that we've come up with. The details are in this paper, which is hidden behind. So memory perturbation equation, its camera ready is still not out, should be out in a week because that's the deadline. So then, but you can find one version of the paper somewhere on the web if you search for it. Okay, so with this, I would sort of close the talk to say I presented three things here. One is uncertainty, another is regularization, and third is memory. And I presented each for each solution. It's sort of a principle to think about these problems. So the first thing is that a straightforward improvement is obtained if you can quantify uncertainty of your parameters well. But then you can use this uncertainty in a regularizer, right? You can use a quadratic regularizer, a weight regularizer, but you could also use different forms. So a form called k-prior uses both the functional form and the parameter form. And then the third one is the memory, is that somehow you also want to make sure that the past is represented well. And for that, you would have to pick points such that they are, somehow points that are that have high prediction error or points that have high prediction variance. Okay, so we've been developing this thing in a project called Base Duality Project, and these are the people. And I'll end the talk by thanking the people in my group. And I believe I have 5 more minutes to answer some questions.
Thank you so much, Emti, for this really interesting talk. Yes, of course, since we started a few minutes late, we're going to run a few minutes over. So there's a couple of questions already for you in the Q&A, so I will ask them and then you can answer them. So the first question is from Camila Gonzalez. She asks, I'm inclined to believe functional regularization is a better option than weight regularization, and replay even better if the constraints for the problem allow it. Why is combining these mechanisms better than only adding functional regularization and replay?
Okay. So one thing that I've learned working on this problem is that there is no, one single answer that is better. So I think I may even say maybe more strongly that if there are people who are pushing for just functional regularizer or just weight regularizer or just replay, and I think this is not right. And you can show this on a very simple problem as well, like what I showed in this slide. Every regularizer, is doing something, but they're not completely able to, reconstruct the gradient, right? So if you did weight regularizer in a nonlinear setting, it leaves some error. Okay, so you may think that somehow doing replay is better, but if you had all the data from the past, fine, then you're right. But whenever you start to have restriction on the memory, like if you cannot store the whole data, then you're actually making some error. And it's the size of the memory that are like the points that you choose and what's going to happen in the future that decides whether this error is going to be enough or not. So I would very strongly say that combining methods is extremely, extremely important. And that's kind of what is written in this paper. If you go and look at this paper, is that if you start looking at EWC, you clearly see what errors are being made. And EWC is a little bit more compact because it's in the parameter space. So you can kind of sum contributions over all data examples, but it doesn't blow up, It still remains the same like size of the parameter. Like if you have 10,000 parameters, then the size of this remains 10,000, no matter how many tasks you have seen. So it's actually a very compact representation. But if you have memory replay style thing, you have to increase the size of the memory. So it's not very efficient. So there are these trade-offs. So I hope that this sort of helps you to look into this issue and convince yourself. Yeah.
Yeah, great. Thank you. I think that was a really nice recap. There's another question from Marty. He asks, in your candidate model in blue, I think this is referring to the last paper in the talk, in the SVM type of diagram, an additional set of support vectors comes into play. So I would think that a candidate set for potential support vectors to be retained might be those exemplars at the periphery of each cluster or each class, or perhaps at least a set of potentially new support vectors exposed with some perturbation of the SVM hyperplane.
Like great point. I think SVM is one of the best way to think about this, right? So you're exactly right. So if you're in the SVM case, because the problem is convex, there's only one representation. So you have representer theorem that tells you that the weights can be represented exactly by like a finite number of sparse, support vectors, right? And because the problem is convex, there's one-to-one thing between them. But for non-convex problems, there is no such representation. And this theory that we are developing here is really developing a representer theorem for non-convex problems. So the word memory is actually used with a lot of thought, and you will see in the future some papers that we are writing, we're connecting it to how representation in psychology works. So I think in general, representative theorem is kind of hard to write and difficult to characterize. And one way that we're doing here is to write about sensitivity. So we're basically saying that sensitivity measure going in that dual space of sensitivity is another way to characterize this. So you're exactly right in saying all of these things, but the difficulty is in going into neural network and other models where I think this sensitivity viewpoint pays off. I hope I answered the right question that you were asking, but if not, I'm happy to hear later more about this. Do I have another minute to answer something, or am I?
Yeah, I think there's one last question, so we'll finish up. Marty has another question that is it that weight space regularization helps to retain some of the sense of the data distribution that was involved in the original training? Yes.
So I think weight space is, we shouldn't give up on weight space because it's somehow, it already does some work. And I would suggest you to read the K. Pryor's paper because these things are kind of mathematically more laid out there. Like this term here is somehow a second order Taylor approximation, right? So the things that are not there in that Taylor approximation is the error. And it's with nonlinearity, that error has to be reduced. And so on top of it, if you add some memory replay, you're able to reduce it by increasing the memory size. So you're right in this thought. I mean, as a Bayesian, I know it's a Gaussian approximation, so that's what it does. So it's actually very clear what kind of mistakes is being made there. Anyway, but that's I'll close with that.
Perfect. Thank you so much, Emti. Thank you for this great talk. And also we want to thank Emti for all of his hard work being our pre-registration chair, so helping us accept some of those pre-registration proposals that will further turn into papers. So thank you again for all of your help with the Unconference. We were happy to host you today.
Thank you very much. Thank you for having me.
Thanks.